The session is being recorded. All right. So do you have any special question that you would like to ask?
No, not really. I've been
Okay.
understanding the material.
Okay. All right. Fine. No problem. I'm going to go through uh, the topic for this week, and I'm going to pull it up. All right. So we are in week 5. Okay. All right. So this week we are going to talk about basic concepts in probability. And we're going to talk, first of all, about the whole purpose of using probabilities. We use probabilities a lot in statistics. In fact, now we use probabilities a lot. Probability distribution is the foundation of statistical analysis. And in particular, it is the foundation of inferential analysis. We talked about inferential analysis and also descriptive analysis. And so descriptive analysis simply summarizes the data and just show you averages, deviations, different kinds of dispersions, so to speak. And, provides you tables so you can essentially see a summary of what the data is. But what do they represent? That is the area of inferential statistics. Okay, are they meaningful? And what do we mean by meaningful? Do they represent a particular characteristic? And if so, to what extent do they represent a particular characteristic? For example, to what extent does the data represent the mean? To what extent does it represent the standard deviation? To what extent does it characterize the population from which you collected the data? Okay, how does it characterize the population? For example, if you use the data to calculate a mean, does that mean actually come from the sample, from the population that you collected the data from? Are you, looking at the mean for a different population? So this is what we will begin to lay the foundation for. Okay. Probability distribution is the foundation for inferential statistics because we use samples. And so when we take samples, we ask ourselves, what is the distribution of the population? And does the sample represent that distribution? So now, when you think about probability, we have two kinds, probability. We have discrete probability distributions. We have continuous probability distributions. And discrete probability distribution is where the values of variables are represented or measured only in what we call quantum in quantum form, in quantum form. And quantum, that is, in discrete form. For example, the data is represented as 1, 2, 3, or 4, or 7, 18, 21, something like that. But there is no value between between any two adjacent values. Okay. For example, if you think about say where people are born, somebody's born in the Bronx, somebody's born in Manhattan, somebody's born in Queens. Okay, and you represent them as 1, 2, and 3. 1 is for anybody that is born in the Bronx, 2 is for anybody born in Queens, and 3 is for anybody that was born in Manhattan. There's no value between 1 and 2. okay? If you measure potholes, for example, along a street, there's one pothole, two potholes, there are three potholes, there are four potholes, and there are five potholes, okay? So you cannot have 1.5 potholes, and you cannot have 2.5 potholes or 2.25 potholes. No, there's nothing like that, okay? So this is the kind of thing we call discrete data. And discrete data can only be represented in a discrete probability distribution. Then we have continuous values that are represented by continuous probability distribution. Between any two adjacent values, there is an infinity of possibilities. For example, between 1 and 2, you can go to 1.000001, 1.000002, 1.000003 until you get to 2. And between 1 and 2, you can have an infinity of possible values. So those are continuous values represented in continuous probability distributions. Now, so just give me a second. Let me see if I can pull up some information that we're going to use. Okay, I'm going to share some file with you. All right, so this is an illustration of discrete probability distribution. And now, any kind of event can be represented in a discrete way. For example, travel time. Suppose you just represent travel time. Travel time is actually continuous, but we can represent it using a discrete probability distribution, making the heroic assumption, for example, that there is no value between any two adjacent values. For example, travel time, 11 minutes, 10 minutes, 12, 13, 14, 15. But let us take this travel time. Let us take this thing here we call travel time. Let us call it potholes on the street. Okay, so these are potholes on the street. Okay, there are 10 potholes, 11 potholes, 12 potholes, 13 potholes, 14 potholes, or 15 potholes. And so you go from street to street and ask yourself, how many potholes in the street? Okay, now there cannot be 1.5 or 10.5 potholes. In this instance, we're looking at a situation where we are saying there were not fewer than 10 potholes. So there are only 10 or 11 or 12, 13, 14, or 15 potholes. And so you represent it in a probability distribution. And here we are saying that 10% of the places that we saw had 10 potholes. And so on the right side is the probability of T. And we said that 15% of the places we saw had 11 potholes. And so these are just percentages, okay? And so you can say they are proportions. Say, 20% of the places we saw had 13 potholes and so forth and so on. So, or you can say last year there were 10 potholes on this street. This year there were 11 potholes. 2 years ago there were 12 potholes. Or the number of years we've been looking at potholes. 20% of the time there were 13 potholes after the season. All right. So now you can go from discrete probability distributions to continuous probability distributions. And this is where we are going to base our class. It's going to be on continuous probability distributions. But for today, let's look at discrete probability distributions. So when you have a distribution like this, what do? You can use it to make estimations. And I'm going to look at your class example in order to provide an estimation. So I'm going to stop share this. And I'm going to pull up your class. Let's see about that. Okay, so this is what we have for this week. Okay. All right. Now, here is a problem here. Okay. And again, here we are looking at what we represent as what do you call it? A discrete probability distribution. Okay. And here we have speed, and we have what is the frequency? How many times did we observe cars that were going at 45 to 55 miles per hour? How many times did we have cars that were going between 55 and 65 miles per hour? And so forth and so on. And so now we say use this table to prepare a relative frequency distribution. So now you convert this to percentages, okay? And so what do you do? We're going to go through the process where we represent the percentages. So I'm going to take this information, put it on a file. All right. So um, how many vehicles were here? That's how we find out the percentages. I'm going to just erase some. Was all right. So there are 375 vehicles here, and so we calculate P of X. Okay. And so the probability of X being equals H5 divided by dollar H $9. So we divide the number of vehicles for each speed range by the total number of vehicles. Okay. Okay. So we'll convert this to percentages if it suits you. All right. So 30% of the, excuse me, I have to stop share this. Sorry. And I have to pull up the Excel file. Okay, so as you can see here, are you seeing my screen? Hello?
Yeah, I see it.
Okay, so as you can see here that 30% of the vehicles had speeds, between 45 and 55. Essentially what we did, we took 150 and divided it by 500, okay? And then we took 225 and divided it by 500, and we took 75 and divided it by 500, and so forth and so on. And so we get a relative frequency distribution of the number of vehicles at each speed range, okay? So what is the next question? We're going to see if I can copy the next question. All right. It says, I use this table to prepare relative frequency distribution. Now, if cars that exceed 65 miles per hour are issued tickets, what percentage of cars will receive tickets the next year? If cars that exceed 65%, 65 miles per hour are issued tickets. So we see that cars that exceed 65 are from 65 to 75 and 75 to 85. So 15% plus 10% will receive tickets each year, okay? So that's how to address that kind of problem. So 25% of vehicles will receive tickets the following year if cars that exceed 65 miles are issued tickets. Now, if the average ticket is $85 and it is expected that 320,000 cars will pass the road next year, how many cars are expected to receive tickets? Okay, so we said 25% will receive tickets, and 320,000 will 320,000 vehicles will pass through this road next year. And so how many cars will 220,000 cars in the state will be, be passing through the roads. And so if 25% of them will receive tickets, then how many tickets will be issued? That will be equals 0.25 times 320,000. And so we're expecting that about 80,000 vehicles, will receive tickets. And so you can now use these 80,000 vehicles that you expect. Now remember that this is an expectation. It may be less than 320,000 cars that pass, maybe more than 320,000. But what you're trying to do here is to provide an estimate. And this is how the government is run. You provide estimates and use those estimates to make a budget. Sometimes the amount of money you receive will be around what you say. It may be a little bit more, it may be a little bit less, and expenditures might be a little bit more or a little bit less. But look, here we're trying to look at revenues. How much do we expect to receive? And so you take 80,000 and multiply by the average amount of a ticket, okay? So this is essentially what what we consider, what we call discrete probability distribution, where you have the numbers, the values of the variable, they come only in whole numbers. They do not come in proportions or fractions or what have you, and you simply assume that the values are discrete, okay? So this is what we are doing this week, the elements of probability distribution. Now, I've just limited this lecture to these elementary concepts because we are going to use only these elementary concepts to do our work for the semester. And then next time we will talk about continuous probability distributions, and then use continuous probability distributions as a foundation for the rest of the class. And it's going to become more and more interesting. It's not going to be this rudimentary anymore as from next week. And I will urge everybody to try to come to the lectures so that we will not have issues with understanding the concepts or doing homework assignment problems. So having said that, do you have any particular questions that you want to ask?
No, thank you, Professor.
Okay, all right. So I'm going to pause this. Next time, I'm going to urge as many of you as possible to come in so that we're going to really do some real serious problems. All right. So
Okay,
thank you for coming.
you.
All
Thank
right.
you. Have a good day.
You too. Bye.